Let's look at tangent planes and areas for parametrized surfaces. We've got a parametrized surface here, so it's a surface in three-dimensional space. And the new way that we've been investigating describing such a surface, and the essential way if you're going to integrate over it, is to parametrize it. In other words, have some function r of uv, and explicitly that's going to be a vector valued function with components x of uv, y of uv, and z of uv that takes some point in UV space. So this is, you can think of this as kind of addresses, some formal description of how to label the points on the surface, and produces for any particular address label u comma v. It produces the actual point over here with coordinates x, y, z in the surface. And if we're going to integrate things over this, if we're going to find the surface area, or if we're going to integrate a scalar function, which would be useful, for example, for finding the mass of a shell of variable density, or if we're going to look at a fluid flowing through, that's going to be the most interesting thing, a vector field flowing across it, and try to find the flux, very analogously to what we were doing in 2 dimensions across a curve, then we need a precise description of exactly at any particular point, how is that surface sitting in 3-dimensional space? Is it more vertical, more horizontal, is it tilted in some way? And how big is the surface? And in fact, how big is any little part of the surface? And that's all about carefully understanding the tangent plane and also how this grid system gets distorted. So the book does a pretty good job of this, but with an excess of notation because they're supposed to be kind of more rigorous. And I'm going to strip it down and make it hopefully a little bit simpler. So we've got some point on the surface right here. And to talk about exactly what point we're looking at, we're going to focus on what parameter values it has. So we're thinking of it as we've got some parameter values u0 and v0. And of course, one really good example of this that we've talked about is the sphere and theta and phi on the sphere, the latitude, longitude kind of coordinates, or the polar angle and the azimuthal angle. And so that's a particularly good example to think of, but I want to think more generally though. And so we're really talking about the point r of u0, v0. But the way we're going to label it, just like when we're labeling things on a parametrized curve, we really focus on the parameter value. So this would be the analog of the t value. Speaking of parametrized curves, the key to all of this is that each of these curves in the standard UV grid, just the rectangular grid, here, if I look at all the points, say along this curve, so that is a curve where u is variable and v is fixed. And we've already looked a little bit about how looking at that particular curve, we're really looking at the image of this line under this mapping. In other words, all the points that I can get to by fixing that v value, let's say it's this in this example, and varying u. That's just a good old-fashioned parametrized curve from chapter 13. Just happens to be this other variable, could be fixed, it could be variable v, but we're fixing it. And so u is just exactly the analog of the t there. So we're looking at a parametrized curve here. And if I do the other, if I vary v instead, and I fix u, then I'm going to get another curve. So that's going to be this one here. And the key is to understand the velocity vectors of those guys, because, let me draw those in red, the velocity vector of the u variable curve is going to be tangent to this curve, which lies in the surface, so it's tangent to the surface. So that's one direction that's tangent to the surface. And let's say as I go up and increase v and let u constant, let's suppose that kind of cranks down this way maybe, and the tangent vector to that guy, the velocity vector to that one, that's also going to be tangent to the surface. So I've got these two vectors that are tangent to the surface, so that means that they both lie in the tangent plane, and so the tangent plane is going to be the plane that contains those two vectors, and we totally know how to describe that. Our preference for describing tangent planes is to get a normal vector. So we describe how this plane sits in the space, and therefore how the surface sits in the space at this point by a normal vector, n. And we're going to be able to get that from these vectors. Now, what are these vectors? They're the velocity vectors of curves, and so they're given by derivatives. So this one is going to be, we're going to call it RU. So that's just the subscript u as in like partial derivative with respect to u. And that's just going to be, have components dx du, dy du, it's a y, and dz du. Great. And then this one, that's going to be rv, dx dv, dy dv, dz dv. Not surprisingly, I've got 3 output functions, x, y, and z, of 2 inputs, u and v, and all, oh, that should be an angle bracket, sorry. And all 6 of the relevant first derivatives are exactly the information we need here. It's very much like the Jacobian story, and we're going to see when we look in a minute at the area element. It's very, very similar to the Jacobian story. And so the normal vector here, we can use the cross product of these guys. So let's see, I don't want to go too far down. We could use n to be just ru cross rv. Now, one important thing is sometimes we're going to need a unit normal vector. And this is not yet normalized. It's not unit length yet. And in some cases, we're going to need to divide this by its magnitude to get a unit normal vector. Often, though, it's actually not that necessary to do that. And if all you care about is saying, hey, what's the normal vector to this tangent plane so I can get the equation of the tangent plane, all that kind of stuff, then this is perfectly great. Okay. The other issue is that this is going to point in a particular direction. And when we do flux integrals, this is again an analog of what we saw in flux across a curve in 2 dimensions. It totally matters whether we use a normal vector like this and a normal vector like this. How that matters is that when we say this surface has exactly this normal vector at this point, we're going to declare, let's use one more color, that say a vector field like a fluid or something flowing through, generally, believe me, trust me, that's orange and not red. But anyway, if you had a vector field going like this, and it's generally in the same direction as n, I should have a vector here. If this is our vector field f, then we're going to count that as positive flux, otherwise it's negative. And so choosing this or flipping this is going to affect the signs of those calculations. So that's 2 subtleties about this. Notice that I took RU cross RV. Somebody might say, why not RV cross RU? It totally works, but it will flip the normal vector. So we're going to just have to be careful about that on a case-by-case basis. Usually what you do is you just go ahead and crank this out and then look carefully. Hey, is this pointing in the direction I really want to be pointing in? Now, so that's how to get the normal vector. And then once you've got a normal vector, and if you've got the x, y, z coordinates of this point, which are going to come just from evaluating x, y, z at u0, v0, you're going to be able to do, just like in chapter 12, how to get the equation of that plane. And we'll practice that, and I've already got examples for that. What about area, though? So there we want to look at another thing about the cross product. Here, all we've used about the cross product is that its direction is orthogonal to the plane that we want. It's orthogonal to these 2 vectors that make up the cross product, and therefore it was perpendicular to the tangent plane. So now we're going to look at this. We're going to take this point, and what I want to imagine is this actually is a very microscopic grid, and that the amount of grid spacing here is an infinitesimal amount du, and the amount of grid spacing here is an infinitesimal amount dv. And what I want to do is I want to figure out if I chop up this surface into little bits that are based on the image of this grid under this map that's going to distort and maybe make things bigger, stretch it, or shrink it. I want to figure out what the area of this little piece of the grid on the actual surface is compared to the area of this one. Well, this is just du times dv. And I want to know what the area of this guy is. So, and this is where I'm going to just redo the picture real quick. Oh, I forgot. It bleeds through. Okay, but this should be good enough. Okay, so now I'm going to zoom in a little bit and make this, I'm going to make it look bigger, even though I want to think of this as a very, very, very small bit of a grid, infinitesimal little bits. And so that goes over to the surface. And if this is small enough, then actually I shouldn't have drawn it as so curved. Then I'm going to get something where this is not actually curving very much. So I'm going to let it curve a little bit. But this is very, very close to a parallelogram. Okay, if you take a map, this is the key thing about how derivatives work, and you're looking at a map that takes 2 dimensions to this 2-dimensional surface inside 3 dimensions. When you magnify it enough, it's going to look linear. It's going to look like a mapping that doesn't do any squares or sines or cosines or anything, and is just linear, just multiplying by constants and adding. And one of the properties that that has is that it's going to take a parallelogram, this is in fact a rectangle, into something that's a parallelogram. Now it's not perfect if du and dv have some finite width, but it gets perfect in the limit. So that's something that we haven't talked about a lot, but that's the one key thing that you need to trust, is that this is really going to be a parallelogram. And I know a very good approximation to the sides of that guy. Okay, so remember, this was a curve. This was the u variable curve. This was the v variable curve. And this vector here is going to be what happens if you follow that velocity vector, ru, and then you follow it for a time, du. It's just starting here, that goes here, this guy goes here, and it's just distance equals rate times time. Or really, displacement is velocity times time. I let the time variable, which is the u here, crank for du, and then the displacement I undergo, to a very good approximation from this corner of the parallelogram to this one, is just this times that amount du. Okay, so that's this displacement vector, and I'm going to take that, and then I'm going to say, oh, this one is where I let v increase. So I'm looking at the velocity when I let v vary, times dv. And those are the 2 vectors that make up a parallelogram. And if I want the area, once again, the crucial thing is to cross them. All throughout, the whole deal is crossing these 2 guys. Ru cross rv is the thing that absolutely controls everything. And so let me just factor out the du dv. So we get our new friend, but hopefully getting a little familiar, Ru cross rv times du dv. Okay, oh, and this is the absolute. This is the magnitude of that vector. Okay, and that is going to be what we would call the scalar surface area element. That is going to be the area of this little bit of the surface. Therefore, for example, and we're going to use that for not just straight up surface area, but more interesting calculations, but the area of the surface is going to be add up all those little bits of surface, all the little ds's, for all the little grid squares here. So coming back to here, we do it for this, and this, and this, and this, and this, and this, over the entire domain that describes the surface, so that's all of D, and that's going to give us the area here. This should start to look a lot like the change of variable situation, because it really is a generalization of the change of variable situation. We're trying to integrate here in the xyz space, and we're basically doing a change of variables back to u and v. We expect a Jacobian factor. We expect a stretching or shrinking factor that can vary from point to point. In fact, essentially, this magnitude of the Ru cross Rv is very much acting like a Jacobian factor. So you should definitely think of it as analogous. So we're going to actually integrate over the parameters, the d, and we're going to integrate exactly this funky Jacobian factor. What's an r? du dv. And that's going to give us the integral over the surface of all the little bits of surface, and that's the area of the surface. Okay, and then we'll have some examples.